What's happening, y'all? Welcome back. We're at the end of our proof that the coefficient matrix arising in the linear algebraic nodal analysis algorithm, the matrix K equals to AR transpose times G times AR, is indeed non-singular. In step 4, we're going to show that the matrix A sub R comes from deleting one column of the incidence matrix corresponding to the deactivated resistor circuit, which for almost all circuits that we will ever consider can be modeled by a directed graph. Thus, we're going to delete one column of an incidence matrix associated with the directed graph. We know from our results in graph theory that the number of linearly independent columns associated with an incidence matrix modeling a connected graph is 1 minus the total number of columns. Well, those are the columns that fill this matrix A sub R. Thus, this part 4 extension video to step 11 is going to show that the rank of A sub R is equal to n, confirming that the matrix K is non-singular. Before we go into the details on this, I want to zoom way out and recall the general structures that we have as we've approached this algorithm and as we set up this proof. Remember, in steps 1 through 5 in our algorithm, we basically translated the circuit that we started with, containing only resistors, voltage sources, and current sources, into a set of matrices, vectors, and equations. In steps 3 and 4, we set up our entire incidence matrix A sub G, where the columns of A sub G correlated with the nodes of our circuit, the edges of A sub G correlated with the elements in our graph, and then we also enumerated edges so that we can partition this matrix based on element type. We had the entire resistor subblock, the entire voltage source subblock, and the entire current source subblock. In the vector of voltage drops across each element, that was also partitioned by element type with the same number of rows correlating with the original incidence matrix. So we had the voltage drops across the resistors, unknown quantity. The voltage drops across the voltage sources, known quantity. That's an engineered set of values depending on how we define those voltage sources in our circuit. That's why it's in blue. And then we had the voltage drops across the current sources. That also is unknown. For the currents running through the elements, we had the currents running through the resistors, unknown. Currents running through the voltage sources, unknown. And then the currents running through the current sources, that was an engineered known value. In step 5, we found ways to combine this information, and we could do that prior to grounding. In fact, that's what we've done here. We said that the KVLs in node potential form stated that each voltage drop across an individual element was the difference between the node potentials on either side of the element prior to choosing ground node. That had individual component-wise realization. So the voltage drops across the resistors was the resistor subblock of the entire incidence matrix multiplied by the vector U sub G. Similarly, the voltage drops across the voltage sources was A sub Vg times U sub G. And then the voltage drops across the current sources were A sub Ig times U sub G. This second equation, the right-hand side is known. Here in red, neither of these values is known because we don't have that information to start with, but based on the definition of the values of the voltage sources, this thing is actually a general linear systems problem, which means there are redundancies between the individual elements in this node potential vector, and we'll talk about eliminating those later. However, starting from these KVLs, we could actually combine those with something called BCRs, or in this case, Ohm's law. So Ohm's law states that the current running through the resistors are going to be the conductances times the voltage drops across the resistors. But from up here, we knew that we could write the voltages as a matrix vector product with the node potentials. Moreover, Kirchhoff's current law says that the sum and difference of all currents entering and leaving a specific node is equal to 0. We can write that in matrix form and then use the subblock partition of each of these matrices in order to write that in summation form. Everywhere we see the vector I sub R, we can substitute that back with the two other equation types, and that allows us to combine all three of these equations into a single system, which looks like this. This system is ungrounded grounded, so we have not yet chosen ground node, and in the matrix U sub G, there are dependencies between the actual entries that arise from the voltage sources. The major idea behind the linear algebraic nodal analysis algorithm is to partition the individual entries of the vector U sub G into two separate types of nodes. One of those we'll call independent node potential variables. For each ordinary node, there is one independent variable. And for each generalized node, there is one independent variable. The second type of node variable we're going to call dependent node potential variables. We have one dependent node potential variable for each voltage source in the entire circuit. And then we have an additional one dependent variable or additional constraint, which is grounding the circuit, choosing one of those potentials to be 0. In step 6 of the LANA algorithm, we discussed the definitions of ordinary and generalized nodes. And then in step 7, we talked about the concept of grounding the circuit. The major idea of making these partitions for the entries of U sub G is to reduce all entries of U sub G into a minimized set of independent nodes, which we'll just call U, where the number of independent node potential variables is the number of nodes in the original circuit minus the number of voltage sources minus 1 for ground node. Throughout all of this work, we figured out how to reduce the individual entries of U sub G down to a minimal set, but we also introduced matrix equations to track those reductions throughout all of our matrix and vector structures and realize those as a linear systems problem. In terms of the individual vector U sub G, that reduction ended up with a vector U. In terms of the matrix equation, we structured this in such a way that this disappeared, and then we forced the matrix A sub RG to turn into the matrix A sub R, realizing a similar reduction in the columns of the matrix A sub IG. With that in mind, we're going to claim that the reduction of the resistor subblock of the entire incidence matrix down to the maximally deflated resistor subblock A sub R happened using two different processes. One of those had to do with the placement of voltage sources in our circuit. In other words, the structure of the complete solution to A sub VG, UG equals V sub V. That's a general linear systems problem. And the other reduction had to do with our choice of ground node when we set one of our node potential variables to 0 by grounding the circuit. In fact, the observation that there are two different reductions happening lead to two different strategies. The first method that we actually use in the linear algebraic nodal analysis algorithm is to first ground the circuit and produce the grounded node potential vector. That happened in step 7 in our algorithm. And then second, we delete all redundancies in the entries of our grounded node potential that occur due to the voltage sources. That was really the focus of steps 9 and 10 in our algorithm. The reason that I took this approach in method 1, the reason that I thought that this was a really nice approach is because it gives an explicit connection with the modified nodal analysis equations. However, we could have also reversed those processes, and specifically we could have deleted all redundancies in the entries of U sub G that arise due to the voltage sources first, and then after we deleted those redundancies, we could then ground the circuit. This second method is really nice because it leads to a direct proof that A sub R has full column rank. The first method is really nice because it leads to a direct connection with modified nodal analysis, which is a very famous algorithm in electrical engineering and is worth the extra time for electrical engineering students who are going to go on to more complex circuit analysis classes. What we're going to show in this video is that these two approaches are identical, and in fact, no matter how we form the matrix A sub R, the end result is the same. Thus, A sub R for sure has full column rank. With that in mind, let's do a quick review of method 1 in our process. In method 1, we start by grounding the circuit, which means we choose one node potential variable and set it equal to 0. Then we track that reduction in matrix equation. So we reduce the full list of node potentials down to a grounded list with a multiplication on the left-hand side, zeroing out that entry. We literally are deleting it because we're setting the value to 0. Similarly, in the entire incidence matrix, we delete the corresponding column related to the entry of our original vector that got sent to 0, and that's done both in the aggregate and in the subblocks. Once we've done that, we solve the grounded voltage source GLSP, which comes from the second block. So if I was looking at A sub V naught times U sub 0 equals V sub V, this is a classical general linear systems problem. The complete solution to that problem takes the form a particular solution. We're going to call that the grounded particular solution because it has no reference to ground node, plus what we're going to call the complete solution to the homogeneous linear system problem involving the matrix A sub V naught. That is our grounded deactivation matrix D times the minimal set of independent node potential vectors. We can then use this matrix D to simplify and fully deactivate the incidence matrices. That thing has the property that the columns of D form a basis for the null space of A sub V naught. And when we multiply D times AR naught, we get AR. D times AI naught, we get AI. D times AV naught, we get 0. In other words, the columns of D are linearly independent solutions to the homogeneous linear system problem involving the matrix A sub V naught. In the second method of forming the matrix A sub R that immediately shows that that matrix has full column rank, we start not by grounding the circuit, but instead by deleting all redundancies in the entries of U sub G that arise due to the voltage sources. In other words, we find a complete solution to the general linear systems problem for the entire incidence matrix A sub VG, UG equals V sub V. Remember, that takes a particular solution. We call that the entire particular solution because this matrix has reference to the ground node, so too does that vector. And then we add matrix Z multiplied by what I call U sub F, and those are the free variables under this linear systems problem. The columns of the matrix Z are going to form a basis for the null space of A sub Vg, which means that those columns are going to correspond to ordinary and generalized nodes. This component together, Z times U sub F, is a complete solution to the homogeneous linear systems problem involving this matrix. We saw a lot more about that structure in the extension videos for step 6, but what I will say is that the matrix A sub Rg times Z is going to encode the incidence matrix of the deactivated resistor circuit that results from setting the voltage sources to 0 and the current sources to 0, taking that resistor network and then modeling it by a digraph. That matrix will actually capture the digraph topology exactly. As long as our original circuit doesn't have two subcircuits that are connected by paths of current sources, we're going to say that that deactivated resistor network is actually a connected graph, which means that the rank of this matrix is going to be F minus 1, or the number of columns of this matrix minus 1. That was the point of parts 2 and 3 of our extension videos to step 11, was to formally explore and argue that that rank theorem must hold. After we eliminate the redundant information having to do with the voltage sources, we can then set a chosen ground node to 0. So out of the independent nodes that are left, set one of those to 0. Just as we talked about grounding the circuit by multiplying by a chosen deflation matrix, we can do that again. We can take the free variables and reduce them to our minimal set by just deleting the one that we chose for the 0 value. And then we can also propagate that through. If we wanted to look at the columns of the matrix Z, those columns correspond to either ordinary nodes or generalized nodes. Whichever node we choose as the ground node, we can delete the corresponding column of Z and form the grounded deactivation matrix whose columns correspond to the non-ground independent node voltage potentials that we've chosen after those two elimination steps. This leads to a slightly reduced version of our complete solution where we have no reference to ground in that representation. We're going to claim that the matrix A sub R that we used in LANA algorithm actually comes from multiplying the original A sub Rg times this grounded deactivation matrix D sub Vg, which another way to say that is it's A sub Rg times Z times D sub F. But remember that A sub Rg times Z is going to be an incidence matrix for a connected digraph model of our deactivated resistor circuit. This matrix D sub F actually just deletes one column from this. From our rank theorem, this is going to have rank F minus 1, and then we're literally going to delete one of those columns. If we can show that A sub r is equal to this, that immediately proves that this matrix has full column rank, since it comes from digraph model for a connected graph minus 1 column. This is where our linear algebraic chops come in. Remember, in step 10 of our algorithm, we defined A sub r to be A sub r naught times D. In step 7, we defined A sub r naught to be A sub r g times D naught. And then in step 10, we defined D to be D naught transpose times D sub Vg. We actually built that matrix looking at the interdependencies between the node potential variables in the vector u sub g. However, we know that matrix multiplication is associative, so instead of associating these two together first and these two together second, we could actually look at D naught transpose as one matrix product. Well, this thing has almost all identity columns, except it's missing one. It's missing the dth column for the ground node. The same thing is true over here. This is missing the dth row associated with ground node. When we multiply those together, we basically get the n sub g times n sub g identity matrix, except that the dth diagonal entry of that thing is 0. That's what that particular equation says. We know in matrix multiplication we have left and right distributivity of matrix multiplication over matrix subtraction, which means I can actually bring that d sub vg in. The identity times d sub vg is just d sub vg. Here I've got an outer product involving an elementary basic vector, so this is actually going to be an elementary matrix unit with almost all 0 entries. There's a single non-zero entry in the main diagonal dth position. So I'm going to multiply that outer product by the matrix d sub vg. But remember that we've said that d sub vg comes from the complete solution deleting the corresponding ground node. But assuming that we do that, literally what we do to form the matrix d sub vg is just take one of those columns, define one of the nodes in those columns as ground, and then delete it. But remember that the columns of the matrix Z were really, really special. For each ordinary node, we have a single column of that matrix that actually has one non-zero entry in the row corresponding to the node number for that ordinary node. And then each generalized node has one column in the matrix Z, where the number of non-zero entries in that column is equal to the number of nodes within that generalized node, and they're actually in the same positions along those row indices. Thus, when we're going to ground our circuit, we just find which node are we going to ground, find the corresponding column where that row entry is non-zero, and then zero that out, and that forms this matrix. But that implies we can focus in on the rows of the matrix D sub Vg. Remember, those rows correspond to nodes in our original circuit. The node that we've chosen at ground, when we look at the entries along that row, they're going to be all 0. By design, we've deleted the information having to do with ground node. It doesn't show up in that matrix. So that means when we're looking at this product, we've just said that the grounding matrix for the deactivated resistor circuit, the one where we delete the column of this where ground node shows up, the dth row of this thing, the row corresponding to the ground node in d sub vg, is going to be the 0 vector. Well, that means when I multiply e sub d transpose times d sub vg, that is the dth row, because this is literally 1 in the dth position, so I'm pulling off the dth row of that. That's going to be the 0 vector. So now this portion goes to 0, and then I have a column vector with a 1 in the dth position, and I'm now placing the 0 row in that column via that outer product, which means that I get the 0 matrix here, which means that this term disappears and A sub r is actually going to be equal to A sub rg times vg, which we've just argued was A sub rg times z times d sub f. But remember, A sub rg times z is the incidence matrix for the digraph model of the deactivated resistor circuit. Here I'm deleting just one column of that. In general, that resistor circuit will be modeled by a connected digraph, so when I delete a column, that matrix has to have full rank, which is the number of nodes in my original circuit minus the number of voltage sources minus 1 for the ground node. The moment I know that AR has full rank, that means K must be non-singular, which means the LANA algorithm produces a non-singular linear system problem in this form. Every non-singular linear system problem has a unique solution I can use that unique solution to produce values of every single node voltage potential, which then gives me all the information that I would want in my circuit. With that, we've just finished a linear algebraic proof that the linear algebraic nodal analysis always yields a non-singular matrix K. I do want to provide a pointer to a different proof of this same fact. If you take a look at a book by Artis Davis, it's called Linear Circuit Analysis. This book, I did a ton of reading to help me figure this linear algebraic nodal analysis algorithm out. In section 4.2 of this book, which starts on page 118, there is a beautiful description of what I would call a scalar approach to nodal analysis, what I might also call classical nodal analysis from the standpoint of electrical engineering. Moreover, at the end of this book on page 1052, there's an appendix B on Telegin theorem, which has to do with the idea of conservation of energy for circuits. The point, though, is that this author actually motivates Telegin's theorem, gives a formal proof, and in fact, as Artis Davis claims, we can use this as a different mechanism to prove that the linear algebraic nodal analysis and classical nodal analysis involve a non-singular coefficient matrix. I haven't formally written those up. I wanted to spend the majority of my time doing something that I'd never seen done before, which was a linear algebraic approach to the proof that this thing is non-singular, and I've just provided that for you. The last thing I wanted to do is give you some specific examples of how this result plays out for our example 2 circuit that we're analyzing. If we take a look at A sub r equal to A sub r naught times D, remember that we formed A sub r naught by deleting one column. So in this case, we started with the entire incidence matrix for the resistor subblock. We deleted the column that we chose as ground, and that led to a grounded resistor subblock. Because that grounded resistor subblock has no reference to the ground node, when we go to deflate it, we delete the corresponding row and the corresponding column in the deactivation matrix that contains ground node information, and that resulted in the fully deactivated and grounded matrix A sub r, which was here. But as we claimed, this was not the only way that we could get to that grounded, deactivated matrix A sub r. In fact, we could have first deactivated the circuit, so taken our entire incidence matrix multiplied by the deactivation matrix Z, whose columns formed a basis for the null space of A sub Vg, the voltage source subblock of our incidence matrix. Notice ordinary nodes 1, 3, and 6 have a single non-zero entry. Generalized nodes 1 and 2 have multiple non-zero entries in the rows corresponding with the node number that are contained in each generalized node. When we multiplied that matrix times this vector, we got the incidence matrix associated with the digraph model of the deactivated resistor circuit. And the claim is we could then delete one column of that. So this matrix models a connected graph. If we delete one column of that corresponding with a chosen ground node, that's exactly what we do here. We delete one column, and that leaves the identical matrix A sub r. I just want to confirm those two matrices are the same, which is exactly the statement that we've just proven. Moreover, because this matrix encodes this digraph, this is a connected digraph. This matrix encodes that information for the connected digraph. So we know this matrix has 5 columns. That means 4 of those columns are linearly independent using our graph theory theorem. But then we choose 4 of those columns. This thing has full column ranks, and we're done. I will say that this took me a little while to figure this out. So I would encourage you watching at home, if you're really excited for learning this fact for yourself, please do use the actual example circuit algorithm as a way to make those arguments, and then refer back to the general proof to convince yourself that the arguments that we're making actually hold for any circuit and any process that we use. With that, we've reached the theoretical foundation of the LANA algorithm, and we're ready to go on to solve the corresponding non-singular linear system and then see how we can use that information to get more interesting information about our original circuit. We'll do that in the next videos.